Yeah. Hello. So
Yeah.
today again we have David, and he will be giving his final talk in his series, a first encounter with diffeology. And today he will be talking diffeological geometry. And yeah, over to you, David.
Okay, yeah. Thank you for the introduction. Thanks one more time for the invitation for these three talks. And it's been a pleasure. Um, so yeah, this talk here, I decided to call it Diffeological Differential Geometry, which is to bring these diffeological ideas, these diffeological objects into the realm of, usual geometry that we're more familiar with. Um, and so just to recap where we are last time, or the two last times, we introduced the category of diffeological spaces, and we saw several examples. And then we also introduced Lie groupoids as, so generically denoted G to M, as well, another model, at least for quotients. So every quotient of a manifold has a natural diffeology, and Lie groupoids can also, in some sense, be used to model quotients. Um, and in particular, then we compared these two approaches and we gave some examples of Lie groupoids whose Morita class, or the collection of groupoids that are equivalent to it, is determined by the quotient itself. So I'll just say Morita class by the diffeological quotient. So in some cases, the diffeological quotient at least contains as much information as the groupoid. Now, I hadn't planned to get to some infinite dimensional geometry, and that will come up today. So I think we'll have to begin with a small interlude before the main content on infinite dimensional structures. So we'll do a brief interlude on infinite dimensional uh, geometry. So what I mean by infinite dimensional geometry is the theory of infinite dimensional manifolds. So we have, vector spaces. Finite dimensional ones are used to model finite dimensional manifolds, and we can use infinite dimensional ones to model infinite dimensional manifolds. Of course, in finite dimensions, it's a bit unambiguous what the smooth structure and topology of a vector space is. For infinite dimensions, it's a lot more subtle. And so the building blocks that we'll use are Frechet spaces. So a Frechet space is, well, it's an infinite dimensional vector, well, okay, finite, I guess, or infinite dimensional vector space, which is a topology, so it's a topological vector space. And just to recall, let me get this out of the way. Whoops. Sorry, I tried to move this and then I paused. Okay. Uh, there's a topological vector space. So just remember, this means that the addition, all right, so I'll denote it E, sorry. Topological vector space E. So that means that the addition and the scalar multiplication are continuous. okay, whose topology is generated by a countable collection of seminorms. So a seminorm is like a norm, except that we drop the definite condition. And in that case, the topological vector space is also called locally convex. So its topology is generated by a countable collection of seminorms. And then moreover, so if it's a topological vector space whose topology is generated by a countable collection of seminorms, we already call that a locally convex topological vector space. But for Frechet space, we will also require it to be, well, Hausdorff, but more importantly, complete. So complete here, meaning that Cauchy sequences converge. Okay. And so for example, so for some first examples of these, uh, we have finite dimensional vector spaces. And more generally, we have Banach spaces. So remember, these ones have a single norm that generates the topology. You don't need semi-norms and you don't need a countable collection of them. So these are complete norm vector spaces. And here we can use the locally convex structure to get two topologies. Two diffeologies on a Frechet space, or more generally, a locally convex topological vector space. But I will stick to Frechet spaces here for time. So there are two reasonable diffeologies to consider. One is going to look a lot more reasonable than the other. So two diffeologies. There are two diffeologies we can consider. So one of them, which I'll denote, let's say on E. So there are diffeologies on E. So D linear. This will be, well, in some notation, I'll use pi LER. So L of ER would be the continuous linear functionals. So I guess I could have also written pi E dual. And pi is supposed to represent some process we can do to a collection of functions. And I'll define this notation by just giving you this set. So this is so this is a notation D-lin, and I need to tell you what the plots are. So over some the plots with domain U will be those maps such that well, here we're going to use the linear maps to test smoothness. So we can take a linear map and apply it to P. Well, this will be a map from U now to R because these are linear maps, linear functionals, really. So such that this thing is smooth for all, sorry, I'll use a symbol, continuous linear functionals. So that is continuous linear functionals. Here R is carrying its usual topology. Oh, and this, sorry, I don't know why I put the scalar multiplication like this up here. I'm just seeing that now. Sorry. All right. Okay. So here R carries its usual topology, so then the definition of continuous is unambiguous, and we take all the continuous linear functionals, use those to test for smoothness. We could also call this scalar-wise smooth. And two, we have another diffeology, which I'll use CONV for convenience. And this one here, I'll define right away on the plot. I'll define the plots right away. So these would be the collection of U as a collection of P, so that, well, here's how we'll probe smoothness. And again, this might seem a bit unnatural at first. Um, we'll probe smoothness by using the smooth curves. And the reason is that somehow, at least with a locally convex topological vector space, the notion of smooth curve can be defined in a rather straightforward way, the way you would normally define a smooth curve. And then we can bootstrap up to a notion of smooth plot from that. So P, though the plots will be all P, such that this map C, which I'll define to be POC tilde from U to R, from R to E, I'm going backwards, is smooth. Or I'll say a different word because it gets a bit confusing. Infinitely differentiable for all smooth curves C from R to E. But now I need to define what smooth curve means. C tilde from R to E. Mm, sorry, I'm mixing up all my domains and codomains here. Sorry. If I'm going to do PO C tilde, then C tilde has to go from R to U, and I don't need to define smoothness. Okay. And here, infinitely differentiable means, well, we'll say that C is infinitely differentiable if one, well, its derivative exists. So this would be like its first derivative. I'll use C bracket 1 for that. It will be viewed as a curve from R to E, and it will be this map, the usual difference quotient. If this thing exists, and then two, we recursively define Cn, and we want that to exist for all naturals, right? So we begin with we consider the notion of, in this case, of smooth curve primitive, and this difference quotient is the usual difference quotient that defines the derivative of a curve. This limit is unique because the vector space is assumed Hausdorff, and this, uh, yeah, because it's assumed Hausdorff. Um, and so then we have a notion of infinitely differentiable curves. And then for the plots, which go from higher dimensional domains rather than just R, we say that these are plots if they're smooth along the curves. And this notion of infinitely differentiable curve, of course, is the usual one if E is an open subset of Rn or if it is Rn itself. Now, these are two diffeologies that we could consider. And in general, they're going to be different. Now, for Frechet spaces, these are the same. This could be, you can see this in maybe Google Meet or 97. That's their big textbook on convenience analysis. Yeah, so for Frechet spaces, these are the same, which means that if I have a Frechet space, I can assign a diffeology without ambiguity. I could take dlin or dconv. And I want to mention that even for E equals Rn, this is a meaningful statement. This is Bowman's theorem. Um, yeah. So this is 1967 by Bowman. So just to get a sense of what I mean by this being a theorem, so for E equals Rn, d lin is the standard diffeology. Or like it's clearly the standard diffeology because our linear functionals from Rn to R, well, it's generated by the projections. And so then we're really saying that a P is smooth if its components are smooth. Um, but for deconvenience, this notion of smoothness is a priori different. We're saying that a map into Rn is smooth if it's smooth along every curve into its domain, every smooth curve into its domain. And this is, a priori a weaker condition. There could possibly be more of these kind of smooth curves, more of these plots than the usual smooth one. So a priori, I could write it as a containment uh, like this. But in fact, Bowman's theorem says that equality holds. So it's a sufficient way to test smoothness. All right, so it's a little surprising fact, which has consequences in diffeology, namely that these two diffeologies are equal. And then just a little remark here. For general Hausdorff locally convex topological vector space, I'll just use locally convex topological vector space E. If E is also what's called phonological, which I won't maybe say what it means, but just emphasize that there's some extra condition, then Kriegel-Mejor call E convenient if this condition holds. Okay. So convenient phonological vector spaces are precisely given by this condition. But we're dealing with Fréchet spaces for now, which are, a bit stricter than this. Okay. And just two examples that are relevant for us, why I took this little digression. If we have a vector bundle, for vector bundle lead M, this would be inside smooth manifolds. I'm not thinking of a diffeological bundle for now, just a standard vector bundle. Um, then we have the d-topology of the space of sections of V. So remind that if the vector bundle is denoted with the map pi, this is a set of all sigma from M to V such that pi over sigma is the entity. So this thing here with its functional diffeology, I ran out of room, sorry. The d-topology of this is equal to its usual Fréchet topology or structure. And by the usual structure, I mean that we can you equip V with some auxiliary Riemannian metric. And then you measure the You say the semi-norms are going to be the derivatives, the size of the derivatives of sigma. So I'll say this vaguely, sigma. So you have the size of sigma itself, and then the first derivative, second, third. So we see there'd be a countable number of derivatives to keep track of. And so we'll get a countable number of semi-norms for this topology. And this topology is the usual first state topology, which coincides with, in fact, the D topology. So this is another way then to define the first state structure without reference to semi-norms, is to use the final topology generated by the smooth plots or by the plots. And moreover, in this case, when we have this functional diffeology here, we could say, well, now there's a third diffeology. We have the usual first state structure, which gives, well, okay, two diffeologies that actually coincide. And then we have the functional diffeology, and we could ask to compare these. So in this case, we give it its first state structure, these two are equal. The two diffeologies defined using the infinite dimensional structure. And moreover, you get the functional diffeology back. And then one more example here, which might come up or not. If we took CK here, uh, for these are now K differentiable functions. We don't assume infinitely differentiable. There's K differentiable for this, uh, which are really the K dimensional, K times differentiable paths in M. So I use P for path. Uh, this is a Banach space. And so then we can equip it with its diffeology, either d-lin or d-con, they're the same. But this one here does not have a natural diffeology sitting around. Um, or at least I'm not going to say this is not a because K is on infinity here, this is not at least a mapping space inside diffeology. So it doesn't have its functional diffeology immediately. So I'll just say this is a mapping space. Okay. So that is what I wanted to mention about infinite dimensional spaces. And now we will go on to a couple applications. Uh, we'll see how much time I have to get through them. It's okay if I don't get through all of them. So I wanted to begin with maybe one of the more approachable ones, which is a singular Serre-Swan theorem as an application. So this section of the talk is based on joint work with Alfonso Garmendia, myself, and Leonid Rivkin this year, or last year, I guess it's 2026 now. Um, and if I say a singular Serre-Swan theorem, then I should tell you I should remind you what the classical one is, the usual one. Uh, so classical Serre-Swan is about the correspondence between vector bundles and C infinity modules. Um, Now, this can be stated in the sort of in algebraic geometry, or it can be stated in smooth manifolds. And we're going to maybe, of course, use the one for smooth manifolds here. So fix M a connected smooth manifold. And then we have this correspondence from vector bundles over M, and we'll get C infinity M modules. And we'll always get C infinity M modules, but for the statement, I'd like to restrict the ones in the codomain of this correspondence. So C infinity modules, modules Q that are finitely generated and also projective. So projective here, I mean that there would exist some other module such that when you add them, you get a free module. Uh, right, so these are two conditions I want to put on my codomain. So the classical Serre-Swan says that this thing here is an equivalence of categories. Sorry, I didn't tell you what gamma is. Sorry. Uh, well, gamma is the section functor, so it's sending V to the sections of V. The C infinity module structure is with pointwise addition, or with fiberwise addition. So I can add two sections by adding them at each point in the fiber, and pointwise multiplication. So scale the section in each fiber by the function f. Okay, so Serre-Swan says this is an equivalence of categories. And the feature of this that I'll spell out explicitly, so in particular, if you're given such a module Q, then it came from a vector bundle V. And by came from, I mean that it's isomorphic to the section space of one of them. It's just Q is isomorphic to some gamma V that you can find. And that's why I restricted the codomain in the first place. Of course, if we just allow for any C infinity module, then we don't expect there to be any kind of vector bundle that whose sections are isomorphic to that given module. And for just yeah, so let's see how badly this could fail. So we will ask, what if Q is not projective? And the simplest example of a non-projective Q would be, let's say Q equals R, but you might say, okay, well, R is a projective module, but we're going to talk about the C infinity R module R. So this will be an extended example. M will be R, and Q will also be R. I guess, so as a module, Q is going to be R with addition. And the C infinity M module structure, or C infinity R module structure, well, the addition is going to be addition in R, so that's not, that's already defined. But what is the multiplication of a function and a number is going to be the value at 0 times that number. So here 0 is a fixed point that I am taking to be able to evaluate the function at, and then I just multiply by q. So here f is inside smooth function. Smooth function from R to R, I'm dropping, when it's functions, I drop the codomain in the notation, and q is just a real number. Okay, So this is the module structure. Uh, and like I said, I want to reiterate that R or Q is R. So Q is a projective R module. That's vector space structure. But here we're not considering Q as an R module. We're considering it as a C infinity R module. So it's not projective as that. And so then what would Serre-Swan, if we were trying to see that the functor is essentially surjective, what kind of thing are we looking for? We're looking for a bundle of vector spaces uh, whose sections are isomorphic to R. And it's a vector bundle over R. So for each T inside R, I need a vector space over that. And then you can imagine, well, for vector bundles, what can I do? I could have zero-dimensional fibers, but then my sections are only trivial ever. The zero section will be the only thing that exists. So I don't get R out of it, I just get the set containing zero. Um, or I could have a one-dimensional bundle, but if I have a one-dimensional bundle, I have a one-dimensional vector space over each point in R. And so I am going to have way too much freedom in the types of sections I have, and I will get something far larger than just distributed numbers. So how do we get something in between? Well, we need some non-trivial fiber, but not too many of them. And in particular, if we were to have such a V, then V should only have one one-dimensional fiber. I'll say one non-trivial fiber, which is one-dimensional. Of course, one-dimensional so that you at least get R here. But you could also ask the same thing for R2 or R3, and then you would need a two-dimensional or three-dimensional fiber. But the point is that you only can really tolerate having one of them. But then this could not possibly be a vector bundle because the fibers of a vector bundle should all have the same dimension. Certainly not a vector bundle. I guess I could say this precise reason. So this violates local triviality. But we are learning about diffeology. And one of the big points of diffeology is that you can have, for example, quotients without leaving the category. So violating local triviality is definitely a problem if you want a vector bundle in smooth manifolds. But if you want something you can take the sections of, some kind of bundle of vector spaces, where maybe you drop the local triviality condition, then the question is this possible? So the point is that we can find such a V inside diffeology. And here is sorry, it's a column. Here is what it is. So we'll define it to be M times R. So the trivial bundle, M, remember, is R in this setup, but I'll just say M times R, quotiented by D, where D is a subset of M times R. And I can tell you what its fiber over T is. So this would be the collection of points in D whose first coordinate is T. This is going to be everything if t is non-zero, and nothing if t is zero. So I guess technically space containing the zero vector space. Uh, and the reason that we take this is, well, we're quotienting. So we want something with a single fiber, which means I should quotient out all of the other fibers and I'll leave the fiber over the origin intact. So D is the thing we're quotienting by. Um, I guess I should just clarify that by quotient D, I mean M times R, quotient by the relation T Q is related to, or sorry, I'll say use V for the vector direction. TV is related to TV prime if V minus V prime is in D over T. Okay, so this is a relation. And I'll draw a picture of this. Well, we would have, maybe I'll draw the M times R. And maybe I'll denote this by E, so I don't have to write M times R all the time. So just E is a vector bundle over M. And then I have inside it D as a subset. So it's these vertical ones here. That's the R components. But then at the origin, I only have the set containing zero. And I quotient it. And so then what I get is that this middle fiber is preserved, but all these others collapse. And this quotient is very non-Hausdorff, right? Because if I take some open subset before I quotient, the open subset of the origin, for instance, will always contain lines on this side and on this side. So it cannot be separated. The origin cannot be separated from this side or this side. And in fact, every point on this fiber cannot be separated from any points nearby. So a neighborhood of this point up here would contain these and a little section like that. So that would be a neighborhood of this point here. And also of this point here, a neighborhood would look like this. But these 2 points in the fiber are not, they are separated. Well, because there's they're not equal. Okay. So this is the kind of thing we can take to have the sections of V to be isomorphic to R. And I thought it would be a bit instructive just to check how this is working. So the claim is that the sections of E, which is a trivial bundle quotiented by this sort of like a sub-bundle, but it's a sub-bundle whose fibers are varying dimension, right? The fibers are one-dimensional, then they drop to zero, and then they're one-dimensional. So the claim is that the sections of this thing is R. And visually, hopefully the claim kind of is believable because what would the sections of this quotient be? Well, the section, so I'll put the, right, so there's still the base manifold R here. This is V, E1, D. D is in the red here. Okay, so we still have the projection of the first coordinate, and that projection survives through the quotient. I can still project out the first coordinate. It's well defined on the quotient because the quotient is sort of taken fiber-wise in the first place. So I'm not moving the fibers around. So it's well defined to project to R in both cases. And so then I have sections which would go up, right? Sections would go up here. So the claim is that the space of sections of that quotient is R. And let's just verify this. I'll do it on a new page. So step one for this would be that in fact, the sections of this are the quotient of the sections. And the map, which does that, so the right side, or both sides are modules. This is a quotient of modules. So this would be, cosets like this, maps to what I'll denote by square bracket S. So that would be take the map S, but then view it as a map into the quotient. So I guess I'm sort of using the square bracket to denote passing to the quotient from E into V. So step one is that this is an isomorphism. And the proof of that, well, at least to do a proof that it's onto proof of surjectivity, because that's, I think, the one that maybe seems a bit non-trivial. And in fact, this is the one that really uses the diffeology, because we're using diffeology to define the notion of section in the first place, of smooth section in the first place. So given some, what do I want to say? Given some section of the quotient, by definition of the quotient diffeology, the diffeology on this, there's some cover, and we can locally lift sigma up to E. So I'll just say that there's a cover and lift sigma I, which fit in this commutative diagram here. Uh, so I have sigma restricted to ui. This is into the quotient. And then we have E sitting on top of that. And we have the lift into E. And we keep in mind that this lift respects the bundle structure because this thing commutes into M. So sigma I is still going to be a section. Yeah, this commutes, and then this is the identity or the inclusion, I guess, map. So sigma I is still going to be a section of E, or at least a locally defined section of E. So we have candidates for the lifts. In other words, we have candidates for the sections of E, the section of E that we're looking for, but these are each defined on a UI, and there's no reason right now that they glue together to be a single section of E. They could differ on the overlaps. But you can resolve this by taking a partition of unity, refining the cover, so you have to be a locally finite one, etc. And we'll get a global section. So given sigma, by definition of diffeology, we have local lifts, and these glue together, we can use into some global sigma tilde. And this will have the property that it is sigma in the quotient. Okay. So that is the first step, is that the sections of the quotient are the quotient of the sections. And by the way, this is a module isomorphism, but it's also a diffeological diffeomorphism. One can check. And because this has a functional diffeology, we can always ask, what about the smoothness of this? So I think I was using notation like this. It's isomorphic in the category of diffeological spaces, as well as in the category of C-infinity modules. Okay. And then just step two would be that the sections of E this is a trivial bundle, so this is just the smooth functions, and the sections of D are what I'll denote by I0, and that is this set of all smooth functions, but f of 0 has to be 0. And we can see this by going back up, sorry for scrolling, a section of D here. A section of D can do anything, but it has to be 0 at 0 because that's the only fiber. So it's any smooth function that vanishes at 0. And then when we make this observation, then of course, this thing here is isomorphic to R. Okay. Now, just some quick notes here. I mean, secretly E was the trivial bundle over R, and D was that specific subbundle. But step one, hopefully when we look at the arguments, didn't appeal to either of those specific facts. So step one holds in the much bigger generality. For E, any vector bundle. And for D, any so-called smooth singular subbundle. And just to elaborate on what that means, so smooth singular subbundle, this would be a subset of E such that, well, over each fiber, now I'll use X for the points in M instead of T, dx is a vector bundle, is a vector subbundle, vector subspace, sorry, of EX. And the smoothness, so that's the singular subbundle because I'm not requiring them all to have the same dimension. The smoothness would be that, just this technical condition here, that there's smooth sections. So for every vector in dx, there exists some section of E which hits V and which is subordinate to D. So it's really a section of D here. Okay. So then this is a generality in which that holds. Sorry. And now, because step one holds in this generality, we're able to essentially give the generalization. We can kind of already see the generalization here. It's that there's an equivalence of categories, but we can expand the right side to include more than just projective things. For example, it's possible to capture R, but we need to work with diffeological vector bundles. But now actually we need to restrict the domain so that we can get the equivalence. So quick intermediate definition. A bundle of diffeological vector spaces V over M. All right, so this is not the main definition is not of this, but I should say what this is. This is a map V to M where you have a smooth addition. Sorry, this would go from the fiber product and a smooth scalar multiplication without local trivializations. So a bundle of diffeological vector spaces V is called a V vector bundle Sepuy of globally bounded rank if V is isomorphic to E mod D for some vector bundle E and singular subbundle D. Okay, so I'll just say as above because I just defined those two things. This would be what we call a Sepuy, a VB Sepuy of globally bounded rank. Now, this doesn't look very intrinsic. It looks like I'm saying it's this thing if these two things exist and it's isomorphic to them. There is an intrinsic definition of VB Sepuy, but I won't give it here. I won't give it here. Now, this word Sepuy, that is not a mathematical term. Well, now it's a mathematical term because we introduced it, but it's not originally a mathematical term. This is from a mountain, sort of a geological formation in Venezuela. It's these mountains that sort of look like this, where you have a savanna and then the mountain comes up like a plateau, very steep sides. And we can sort of see maybe why we called it this. Is because this is what these quotient bundles look like a little bit. Okay,
So the
so
first condition is have smooth addition from V cross our
yeah,
M to V and to M finally.
yeah. Did I say to M? No, to V.
Okay,
That's addition, and that's V. Yeah, fiber-wise addition is smooth.
right.
Sorry. Okay, so we'll just call these things that arise as these quotients VB Tepuy. And then I can give the theorem. I'll put it here. I'll be generous with space since it's an infinite board, really. Uh, so this is my collaborators, as I mentioned. So we have this functor from these things of globally bounded rank to C infinity M modules. And we will still assume, for this specific statement of our theorem, we'll still assume finitely generated. And here, we do not need projective, but we do need something a little weaker, or a lot weaker, depending on how extreme you think the example of the C infinity R module R is, but fiber determined. And here I can also decorate this actually with Frechet, because I can equip the, so this would go from V to gamma V. Now V is secretly, remember, by definition, E mod D, and gamma of V is secretly gamma E mod gamma D. And so this thing, or sorry, gamma of V is secretly gamma of E mod D. This thing here carries this natural functional diffeology, but it's also gamma E mod gamma D. So this thing carries its natural functional diffeology. But now gamma of E, that is a Frechet space because E is just a vector bundle, a usual vector bundle. So I can quotient by a subspace. In fact, it's a closed subspace, and therefore I also can see that the quotient diffeology is the Frechet diffeology. Okay, so I could put the word Frechet there. And the theorem is not just symbols. The theorem says gamma is a equivalence or an equivalence of categories. Um, from these VB Tipui to these fiber determined Frechet modules. And I don't want to just leave the word fiber determined completely undefined. So maybe ending with the theorem is a bit of a high note, but I do need to say fiber determined, what it really does mean. So fiber determined, think of it as the necessary condition to be the sections of a diffeological bundle of vector spaces, not even a VB Tipui. This is necessary to be the sections of any kind of geometric space, a geometric vector bundle. So fiber determined means that for all Q in your module, Q is 0 if and only if the image of Q inside this quotient is 0 for all M, where here IM is those functions. I was using X this whole time sorry, I was using X this whole time for the points in M when M was not just R. So it's X, X, X. So IX is a set of functions which vanish at X. And so we can sort of see that this thing here stands in for the collection of values of Q somehow. If we really interpreted Q as a section, this would be Q of X. And so Q should be 0 if and only if Q of X is 0 for all X. That is the meaning of fiber determined. And so it really is a necessary condition for essential surjectivity. And it turns out that the necessary one is sufficient. We don't need projective. We don't need projective. But we need to relax what we mean by vector bundle or bundle of vector spaces. Okay, so yeah, I hope that this, at least this one example, gives a taste of how diffeology can arise in, again, more usual differential geometry. So it gives a staging ground in what we've seen here to generalize the Serre-Swan theorem, at least. And then some other examples that maybe I don't have time to get to are that you can generalize things like Lee's third theorem for Lie groupoids. And there's also some things you can do for geometric quantization. But I believe that is the hour, so I think this is maybe an okay place to stop.
Okay. So just I will ask one thing. So the theorem that you just said that the vector bundles take you of globally bundled rank.
Yeah.
So like, is it implied that does your theorem implies the classical Serre-Swan?
Yes. Yes. So what happens is that you can apply this theorem and you can have a projective module, and then projective modules are also fiber determined. So then you'll get a VB Tipui of globally bounded rank. Now, yeah, a priori, a VB Tipui is not a regular vector bundle, but you can sort of check that the rank is constant, not just bounded. Now, is it clear from the projectivity that the rank would be constant? Yes, I think so. The rank, I think, will be the dimension of these. Like the rank, so like sort of the rank at each point would be the dimension of these. So you can just check that projective would mean that these all have the same dimension. And then that will then you'll see that you have a vector bundle of constant rank. There is a little lemma to really get Serre-Swan sort of quote unquote automatically from our theorem, which is that if you have maybe I can write it just sort of down here as answering a question. So there's some little lemma which is that if you have a bundle like this, so if a bundle of diffeological vector spaces, again, you assume essentially that you only have the fiberwise addition and scalar multiplication without local triviality. But if you assume that V and M are manifolds, and I think also this is a submersion, which is the case, in our theorem, this will be a submersion. So these are really two things you assume here for this lemma. Then actually, this is locally trivial. Okay, so you apply our theorem to a projective module, you'll get a bundle of vector spaces where the total space and the base space are manifolds and the projection is submersion. Uh, then, in fact, that is always a locally trivial vector bundle. So you can recognize that you're getting a usual vector bundle, and that reproduces Serre-Swan. Um, there's also the question, I guess, of the what happens on the arrows. Equivalence of categories also says bijection on the arrow spaces. That's really at all not that's not an issue at all. Diffeologically smooth bundle maps. You won't get more diffeologically smooth bundle maps for vector bundles than the usual ones.
Okay, thank you. Okay, so any other questions? Okay, so in that case, we'll thank to David for this nice set of lectures. Okay, yeah, thank you again, David.
Yeah, thank you.
Okay, so goodbye for now.
Yeah, bye.